Venting a nitrogen-purged enclosure 15 feet up into the air may not violate the code if the following conditions are met. Firstly, dilution. The flow rate of the nitrogen purge is sufficient to dilute the hazardous gases to below the lower explosive limit, abbreviated LEL, within the 15-foot radius around the enclosure. Secondly, dispersion. The vent height and location are designed to promote the dispersion of hazardous gases away from the work area. Thirdly, air monitoring. Continuous air monitoring is conducted to ensure that hazardous gas concentrations remain below the LEL at ground level and within the 15-foot radius. Regarding the difference between pressurized and purged enclosures, pressurized enclosures are sealed to prevent the entry of hazardous gases. They maintain a positive pressure inside the enclosure to prevent the ingress of contaminants, and they are suitable for hazardous environments where the release of hazardous gases must be strictly controlled. Purged enclosures are vented to allow the flow of gases in and out of the enclosure. They use a continuous flow of clean air or nitrogen to create a positive pressure inside the enclosure. They dilute and remove hazardous gases but may not completely prevent their entry. They are suitable for hazardous environments where the risk of accidental leaks or shutdowns in the purging system is low. In the context of a hydrogen plant, given the hazardous nature of the hydrogen plant environment and the potential for natural gas and refinery gas leaks, it is recommended to use a pressurized enclosure for equipment that could release significant amounts of hazardous gases. Use a purged enclosure for equipment with a lower risk of hazardous gas release, but this still requires protection from the hazardous environment. Conduct thorough hazard analysis and risk assessment to determine the appropriate type of enclosure for each application. Implement continuous air monitoring to ensure the effectiveness of the purging or pressurization system. To elaborate on dilution, it is crucial that the nitrogen purge flow rate is adequate to reduce the concentration of hazardous gases below their lower explosive limit (LEL). The LEL is the lowest concentration of a gas or vapor in air that is capable of igniting in the presence of an ignition source. The effectiveness of the dilution process depends on several factors, including the flow rate of the nitrogen purge, the volume of the enclosure, and the rate at which hazardous gases are released. Insufficient nitrogen flow can lead to a buildup of hazardous gases inside the enclosure, increasing the risk of explosion. Therefore, the nitrogen purge system must be carefully designed and maintained to ensure adequate dilution. Moving on to dispersion, the height and location of the vent play a significant role in how effectively hazardous gases are dispersed into the atmosphere. The goal is to release the gases in a manner that minimizes the concentration at ground level and in the surrounding work area. Factors to consider include wind direction, wind speed, and the presence of any nearby structures that could obstruct or redirect the flow of gases. Venting at a higher elevation generally promotes better dispersion, as it allows the gases to mix more readily with the surrounding air. However, the optimal vent height and location will vary depending on the specific characteristics of the site and the hazardous gases involved. Continuous air monitoring is essential to verify the effectiveness of the nitrogen purge and venting system. Air monitors should be strategically placed at ground level and within the 15-foot radius around the enclosure to detect any buildup of hazardous gases. The monitors should be calibrated regularly and set to alarm if gas concentrations exceed a predetermined threshold, typically a percentage of the LEL. Air monitoring provides an early warning of any potential problems with the purging or venting system, allowing for corrective action to be taken before a hazardous condition develops. Let's dive deeper into pressurized enclosures. Pressurized enclosures are designed to create a completely sealed environment, preventing the entry of hazardous gases or dust. This is achieved by maintaining a positive pressure inside the enclosure, typically using a source of clean air or inert gas such as nitrogen. The positive pressure ensures that any leaks in the enclosure will result in the outflow of clean air, rather than the inflow of hazardous gases. Pressurized enclosures are often used in situations where the release of hazardous gases must be strictly controlled, such as in chemical processing plants or oil refineries. Now let's delve into purged enclosures. Purged enclosures, on the other hand, are not completely sealed. They rely on a continuous flow of clean air or nitrogen to dilute and remove any hazardous gases that may enter the enclosure. The flow of gas creates a positive pressure inside the enclosure, which helps to prevent the ingress of contaminants. However, because the enclosure is not completely sealed, there is still a risk that hazardous gases could enter in the event of a leak or shutdown in the purging system. Purged enclosures are typically used in situations where the risk of hazardous gas release is relatively low, but protection from the hazardous environment is still required. In the context of a hydrogen plant, the selection of enclosure type depends on a thorough assessment of the hazards involved. Hydrogen is a highly flammable gas that can easily ignite in the presence of air and an ignition source. Natural gas and refinery gas also pose significant fire and explosion hazards. Given the potential for leaks and the severity of the consequences, it is generally recommended to use pressurized enclosures for equipment that could release significant amounts of these gases. This includes equipment such as compressors, pumps, and reactors. For equipment with a low risk of hazardous gas release, such as electrical control panels or instrumentation, purged enclosures may be adequate. However, even in these cases, it is important to conduct a thorough hazard analysis to ensure that the purging system is properly designed and maintained. Hazard analysis and risk assessment are critical steps in determining the appropriate type of enclosure for each application. A hazard analysis involves identifying all of the potential hazards associated with a particular piece of equipment or process. This includes hazards related to the release of hazardous gases, as well as other hazards such as electrical shock or mechanical failure. Risk assessment involves evaluating the likelihood and severity of each hazard. This information is then used to determine the level of protection required and to select the appropriate type of enclosure. Continuous air monitoring is an essential component of any hazardous location safety program. Air monitors should be strategically placed throughout the facility to detect any buildup of hazardous gases. The monitors should be calibrated regularly and set to alarm if gas concentrations exceed a predetermined threshold. Air monitoring data can be used to track the effectiveness of the purging and pressurization systems and to identify any potential problems before they become hazardous. Further expanding on the concept of dilution, remember that the goal is to maintain the concentration of hazardous gases below the lower explosive limit (LEL). This requires a careful balance between the nitrogen purge flow rate, the volume of the enclosure, and the rate at which hazardous gases are released. The nitrogen purge flow rate must be sufficient to dilute any hazardous gases that enter the enclosure to below the LEL. The volume of the enclosure affects the concentration of hazardous gases. A larger enclosure will require a higher nitrogen purge flow rate to achieve the same level of dilution. The rate at which hazardous gases are released depends on the type of equipment and the process being performed. Equipment that is prone to leaks or that handles large quantities of hazardous gases will require a higher nitrogen purge flow rate. Let's re-emphasize dispersion. Effective dispersion of hazardous gases is crucial to minimizing the risk of fire or explosion. The height and location of the vent should be carefully selected to promote the mixing of hazardous gases with the surrounding air. Factors to consider include wind direction, wind speed, and the presence of any nearby structures. Venting at a higher elevation generally provides better dispersion, as it allows the gases to mix more readily with the surrounding air. However, the optimal vent height and location will vary depending on the specific characteristics of the site. Continuing the discussion on air monitoring, continuous air monitoring provides an early warning of any potential problems with the purging or pressurization system. Air monitors should be strategically placed at ground level and within the 15-foot radius around the enclosure to detect any buildup of hazardous gases. The monitors should be calibrated regularly and set to alarm if gas concentrations exceed a predetermined threshold. Air monitoring data can be used to track the effectiveness of the purging and pressurization systems and to identify any potential problems before they become hazardous. A deeper dive into pressurized enclosures tells us that these types of enclosures are designed to provide a high level of protection against hazardous gases and dust. They are typically used in situations where the release of hazardous gases must be strictly controlled. The positive pressure inside the enclosure prevents the entry of contaminants, even if there are leaks in the enclosure. Pressurized enclosures are often equipped with interlocks that automatically shut down the equipment if the pressure drops below a certain level. Furthermore, a detailed examination of purged enclosures indicates that these types of enclosures offer a lower level of protection than pressurized enclosures. They are typically used in situations where the risk of hazardous gas release is relatively low. The continuous flow of clean air or nitrogen dilutes and removes any hazardous gases that may enter the enclosure. However, because the enclosure is not completely sealed, there is still a risk that hazardous gases could enter in the event of a leak or shutdown in the purging system. Regarding the specifics of hydrogen plants, the selection of enclosure type should be based on a thorough assessment of the hazards involved. Factors to consider include the type and quantity of hazardous gases present, the potential for leaks, and the severity of the consequences. In general, pressurized enclosures should be used for equipment that could release significant amounts of hazardous gases, while purged enclosures may be adequate for equipment with a lower risk of hazardous gas release. A deeper explanation of hazard analysis and risk assessment is needed. Hazard analysis is a systematic process for identifying potential hazards associated with a particular piece of equipment or process. Risk assessment is the process of evaluating the likelihood and severity of each hazard. The results of the hazard analysis and risk assessment are used to determine the level of protection required and to select the appropriate type of enclosure. Continuous air monitoring, as previously mentioned, is an essential component of any hazardous location safety program. Air monitors should be strategically placed throughout the facility to detect any buildup of hazardous gases. The monitors should be calibrated regularly and set to alarm if gas concentrations exceed a predetermined threshold. Let's touch on some additional considerations for venting nitrogen purged enclosures. Firstly, the vent should be located in an area where it will not create a hazard to personnel or equipment. For example, the vent should not be located near walkways or other areas where people may be exposed to hazardous gases. Secondly, the vent should be designed to prevent the ingress of rain or snow. This can be accomplished by using a vent cap or other protective device. Thirdly, the vent should be inspected regularly to ensure that it is not blocked or damaged. A blocked vent can prevent the proper flow of nitrogen, which can increase the risk of explosion. Lastly, it is important to consult with a qualified engineer or safety professional to ensure that the venting system is properly designed and installed. A qualified professional can help to assess the hazards involved and to select the appropriate type of enclosure and venting system. Furthermore, it is important to note that the requirements for venting nitrogen purged enclosures may vary depending on the specific codes and standards that apply to the installation. It is essential to consult with the relevant authorities to ensure that the venting system meets all applicable requirements. In summary, venting a nitrogen purged enclosure in a Class 1 Division 1 hazardous environment requires careful consideration of several factors, including dilution, dispersion, air monitoring, and enclosure type. By following these guidelines, you can help to ensure the safety of personnel and equipment. Finally, always prioritize safety. Hazardous environments demand meticulous planning, execution, and continuous monitoring. Never compromise on safety protocols. Remember, safety is not just a requirement, it's a commitment.